All right, ANOVA assumptions. Before I start, I will say, assumptions of statistical tests are very important. However, they're often ignored. And one of the reasons why that is because it's become so easy to run a statistical analysis that lots of people are doing it without really much knowledge of the different procedures. A couple of ANOVA assumptions. The first one is really more of an assumption about the sort of conclusions you can draw based on in terms of causal conclusions. If you want to draw causal conclusions, you either have to have random assignment to research conditions or a random sample of people from a representative pool. Um, Random assignment, that's for when you have a factor that represents um, an experimental manipulation. Random sampling is for when you want to compare people from existing categories, for example, liberals versus conservatives. Those are the only conditions under which you can infer causality if you've used these ANOVA type designs. This isn't a statistical issue at all. This is a methodological issue. It has nothing to do with the statistic itself. So that's not really the important one. The one that we will deal with is called homogeneity of variance. For those of you who took the regression class, this is the same as the assumption of homoskedasticity. It's just simpler to assess because we only have two groups rather than points all over the place. As a general rule, no more than a 4-to-1 ratio of biggest to smallest variances when the sample sizes are roughly equal. Remember, the variance, that's just the squared standard deviation. If the sample sizes are unequal, then less inequality of the variance it would be required. I would probably not go over 2.5 to 1 if I had very uneven sample sizes. All right, strategies for addressing the homogeneity violations. One, ignore the problem. You might think, oh, well, people publishing research, they know better. I get submissions all the time where it's clear that there are homogeneity problems that have been ignored. So don't just think because something's published, it's right. There's a test called Levene's test. Levene's provides a significance test focused on whether the variances differ significantly. This is always something that I go on a rant about. Levene's test is so widely used, yet it is awful. People just want something that says yes or no. I want yes or no. The problem with Levene's test is it's really sensitive when sample sizes are big and really insensitive when sample sizes are small. Problematically, assumption violations are the big problem when sample sizes are small rather than when they're large. So this is going to tell you things are fine when your sample sizes are small and things are problematic when sample sizes are large. And it's exactly the opposite of what you want. So Levene's test is no good. 4-to-1 variance rule. That's a solid rule of thumb. It isn't going to work in every single case, particularly when the sample sizes are unequal, but otherwise 4-to-1 is fine. All right, so how do we address homogeneity violations? This is kind of a workaround, and it doesn't directly address them, but it does affect them. We can normalize variables through data transformation. Normality is not an assumption or a requirement. However, normally distributed variables tend to meet homogeneity assumptions more than non-normal ones. Here we would apply one of several transformations and then use those transform variables in our analyses. These transformations include taking the square root, taking the log, taking the inverse, or what we call reflected transformation, when we take something that's negatively skewed, turn it around, and then apply one of these. I recommend these with caution. I would say if your data are measured in meaningful units, then that would be problematic. The example that I give oftentimes is if you're looking at the effect of an exercise intervention on blood pressure, the square root or the log of blood pressure would not be easily interpretable. You wouldn't want to say, oh, well, 3.1 log base 10 units of blood pressure drop for the people in the experimental condition. Yeah, it just doesn't fly. So it's really a tough. It's tough when you have measures that are meaningful. Now, luckily in psychology, we generally don't deal with meaningful measurements. Most of our measures are just, oh, this is on a 1 to 100 scale, so it's not a concern. But do give some thought to that when you're using these. Other strategies, robust approaches such as Welch's. Welch's approach, as we saw with the t-test, simply adjust the degrees of freedom downward, and its adjustment adjust it further and further downward the more unequal things are. Great adjustment. There are approaches that we'll talk about later in the semester that don't require assumptions. There's various forms of what are called robust tests, and what that means is they don't make these assumptions. Bootstrapping, another approach that doesn't make any assumptions. And then finally, the last approach is throwing out the data and trying again. No, definitely don't do that. That would be silly. All right, so screening for assumption violations. I usually begin with a focus on the normality of the variables. Now recall, that's not a requirement, but it does often produce violations. You can do this with various different graphs, box plots, density plots, histograms, QQ plots. I was very disappointed that when we moved to R that it didn't provide what are called PP plots. PP plots are a little bit more interpretable in my mind than QQ plots. Also, I'm immature and I like to say pee-pee. One of my greatest pleasures in this class. We have two commands from the DescTools package, Skew and, I'm sorry, this says Kurtosis. The command's actually Kurt. Skew is the ends of the distribution. Kurtosis is the height of the distribution. Take each of these divided by their standard error. More than a 3-to-1 ratio is bad. And what we can do is we can construct a 99% confidence interval and ask whether 0 falls inside of that interval. If you want to review the different forms of skew, this is positively skewed on top, negatively skewed on the bottom. It's not where the bulk of the data is, it's where that tail is pointing. And I think that's always it's always been a little counterintuitive to me. It's where the tail is rather than the bulk of the distribution. Kurtosis, we have 3 different situations here. Mesokurtic is basically what we would get if we had a normal distribution. Leptokurtic is a distribution that's really, really high up, and platykurtic, a really flat distribution. These are the different ways that things can be non-normal. In general, if you have skew, you'll probably have a problem with kurtosis as well. And I'd like to give a shout out to Twitter for something I saw posted yesterday. Platykurtosis represented here with, of course, platypus. Perhaps nature's weirdest animal.